18, check that you completed the square correctly. That's going to be on the test, so hopefully you're doing this correctly. X minus 1 all squared plus y plus 1 all squared equals 4. From that, you'll need to find the center and the radius. The radius is the square root of that number over there, so the radius is 2. 19. It kind of depends on what part of the curve you shifted, so your answer could be different. But what definitely should be the same for all of us is a 3 either at the front or the back added, a 6 for an amplitude, 2/3 because the period was 540, and then the positive cosine, negative cosine, and the shift could be different depending on how you looked at things. Does anybody want to throw out a different answer? If they want to know if theirs is correct or not, I can tell you that. Did anybody answer something besides the 135 shift? We could also do this. It's the most logical. They had the peak one. Okay. We know 20. You should have a -3 center line. All of us should. You should have a 1.5 amplitude. That's weird. And in this case, the period was 90 degrees, so that means it's really 4 times as fast, so there's a 4 there. And then again, the sine and the positive 30 could be a couple different things, depending on what's there. Okay. 21 is -9 over root 2 plus 9 over root 2i. So for 22, it's just the solutions you see, 3 pi over 2 and pi over 2. For 21, 23, I want you to grade this for 2 points. I am not exactly always seeing the work I would like, so when you go to solve this, you should be saying, get rid of the cosine first. So you should be starting with saying 4 theta needs to be this. I definitely will not take it if it's just a bunch of floating stuff and you didn't tell me this is what 4 theta is. So you should have clearly in your work, 4 theta is, and 8 different solutions. Then, in a totally different step, you should have theta is this. When you divided all those possibilities by 4. That is 2 points. If you fail to show the 4 theta, you clearly label it or find all those solutions, then call it -1 or 2, whatever you need. Questions? Okay, 24. Factors as you see, cosine plus 1 or cosine plus 3. Cosine equal -1 would imply the equals pi. Cosine cannot equal -3, so there's no answer there. 25. Verify that your individual results are correct. Obviously, you had the answer in the back of the book, so 0 doesn't tell me a whole lot. Anybody with vision could tell me the answer is 0. What I want to see is the answer before that. Did you get 1/3 minus 4/3 plus 1/4 plus 3/4? And then correctly to get 0. All right. 26. This is a 3-point problem. First, check that you found the equation of the line correctly in point slope form. It should have been something like y. Oops, what the heck? Y minus 3 equals 2/3 x minus 2, yeah? Do you agree? Okay, so that should have been the point slope form of the line. The intersection points were gross. They were, there you go, boom. Okay, x is 20/13 and y is 35/13 for the intersection point. If you have that, you're good. And then the third point is, did you get the distance right? Either 2/13 over 13, or if you did decimal, what was that about? Anybody do a decimal? All right. 2/13 over 13 is probably about, what, they're close to 8/13. So in the 0.6, 0.7-ish range, I'm guessing. Let's see how close I am. Since you're not helping me, I'll do it myself. Divided by 13. 0.5547. Okay, 27 was a log problem. You had two solutions, but negative 1/2 is not okay in the second log expression, so just 3 is your answer. All right? Yep, I'm sorry. Yes. Yes. Say again. Oh. So 20/13, I feel like negative 6/13 is true squared. And 39 4/13 feels right there. So if your y's, x's and y's were correct, but your distances, check your distance root. Right? It seems like that's pretty right on. It's pretty small. Okay. 28, x is positive or negative 4 initially, but it can't be negative 4, so it's just x equal 4. Always make sure you're taking the log of a positive if you get a solution. 29 is 2 points, 1 for part A, which is 12, 2 for part B, which is 0. If you only missed one of those, then take off just 1. 30 is 2 points. A is negative pi over 3 or negative 60 degrees, whichever you like, and B is negative 1. A is 2 points. First, I hope you factored the denominator so it's negative x minus 4. Really, in essence, then you have 2 reflections, so it's actually turns out to be more like a normal 1 over x minus 4 plus 3. That's a heck of a lot easier than double reflection. At any rate, it's 4 to the right and up 3, so you should have asymptotes of y equal 3 and x equal 4. And then your graph should be correctly bending and reflected the right way, in the right shape, obviously. All right. B is 25 degrees. C is different than this, so I'll do it on the next slide. D is 14.696 is side C, is what you're looking for. Very cool. And E you will have to do on the next slide. Are you ready then to look those over? You're not? Yeah, you are. Okay, so let's see the identities. So I guess I don't know if I mumbled or what. When I say for this to be correct, you should change one thing at a time. But I'll say it again. If this is going to be correct, there should be 1 change per step, not 2. And if you change 2 per step, it is wrong. Always. So if you go to make a change, what one thing do you want to change? Cosine of 90 minus theta. Cool. That's awesome. Cosine of 90 minus theta is sine of theta. Everything else must stay the same. You may not change anything else. Okay? What next would you like to change? The cosine of negative theta or the tangent? The tangent, okay. What's tangent of negative theta? Which is to say, what happens if instead of going up in a positive way, you go down in a negative way? You would get the opposite. Oh, are you replacing sine with tangent with sine over cosine? Oh, okay. So it is the opposite of normal tangent, right? By going down, you change the opposite, which means you change the tangent, and you get the opposite sign. The rest of it must stay the same. All right, now what do you want to change? Cosine of negative theta. If you go up versus down, what happens to the adjacent side? Stays the same, and there's no change. So cosine of negative theta is the same as cosine of positive theta, or normal cosine of theta. Well, you're oh so close to there. I don't know what that says. What is sine over cosine? Tangent. Tangent theta minus tangent theta. At that point, 0 is obviously the outcome. If you got this far, I guess I take it. Really, you should be taking the left all the way until it's the same as the right. All right. If you're not clear on, obviously these steps could be in different order. You didn't have to do it in this order. You didn't have to do the top first, then the tangent. These could be switched. Cool? Okay. Here, ooh, this was a bit of a humdinger. So in my mind, so let's talk strategy here. For the identity people in the know, you kind of want to peek over here and say, where do you want to get to? Cotangent. What is cotangent? Cosine over sine. Now, I'm not working the right side. I'm just trying to say, what do I need to get to? Do you agree that if I can get the left side to be cosine 70 over sine 70, then I'm home free, right? So I want to really focus on getting there, then I'll be at cotangent. So it seems like I want to talk all 70s. So let's start by dealing with the 20s. What's the sine of 20 the same as? Cosine 70. Beautiful. Everything else has got to stay the same. Feel free to grumble under your breath all day long. I don't care. I can't hear it. Okay. All right. So 70s. Cool. This is a 20. We probably want it to be a 70. Let's deal with it. What's it? That equals it. Sine 70. Now we're talking. Cool. Now, did you say, oh, that's so fat, or did you start working here? Now I've started with a negative lecture on you, and now you're afraid to talk. So, what do you say? Katie, what should I do now? Okay. To what? I'm going to leave this stuff. Cosine 70. Okay. So, you're saying change the bottom one to secant of 70. I'm down. Okay. That's good because, again, we're trying to make everything 70-ish, and that's a good step. We took that 20 and made it a 70. Please, can we at some point, are we good? So that's one, yay? Now, you might say, didn't you just do two things at once? And, yeah, I kind of did. In that I made a substitution and I had. I don't really consider that two things at once. In my mind, I just divided stuff out, and that's, I don't know, I guess I should follow my own instructions. So I guess we're going to do it. Dang, darn words coming back to bite me. Okay, so I replaced this, and now I'm going to 1, 1, 1, 1. So now I'm at cosecant 70 over secant 70. You follow? Are you with me? Okay, we're almost there. What can you put in for cosecant? 1 over sine. Cool. 1 over sine theta over secant, not theta, 70 over secant 70. Cool. What can you put in for secant? 1 over cosine. And then, we're all so close. How do you get to cotangent? Flip it, or multiply top and bottom by cosine, whatever you want to do, but cosine 70 over sine of 70 is cotangent of 70. Where? This, from here to here, that's one step. I divided. Yeah?
Well, you have to show it. Yeah, you have to show it.
What do you mean divided two things at once? When I do a division problem, I'm doing a division problem. This is 3 halves. That's not two things at once. That's a dividing. I divided. Yeah? So, yeah, that's, I don't feel like that's two things at once. I just did division. Okay. Okay. Are we good there? Total up how many you missed, and put it at the top, pass it to the middle, and let's move along to the old lesson.
I know it's weird. I know it's weird.
We just let me one part look at the 26 and I'll see if the others. Don't put it back. Thanks, sir. Okay. Binomial extension, yay. I can't actually watch any baseball or baseball or basketball without thinking of binomial extension. Now if you're saying I hate baseball, basketball, then don't worry. So, let me just start with saying this lesson seems like a whole bunch of mindless, worthless symbol pushing, and there can't be any use to it. But actually, the idea of binomial probability is a huge part of probability and statistics. So, although it's going to be on the abstract today, because that's how Saxon does, first he teaches you this algebra concept and later you learn an application. Please just take my word for it that you will use this anytime. I mean, if I ask you the question, hey, I have a test with 5 multiple choice answers, and each one has an A, B, C, D, or E. What's the probability of getting, randomly guessing 3 out of 5? That's this, okay? Binomial expansion. If I say, hey, he's a 70% free throw shooter, comes to the line 10 times in a game, what's the probability he hits 7? That's this, okay? All of that binomial expansion, this binomial expansion idea is very important. We'll get to applications later. Do you believe me? Okay, whatever, okay, just teach, all right? All right, so it goes like this. The idea is when you take a binomial is 2 terms, something like a plus b, or x plus 2, or y minus x, all those stuff. It's really just 2 algebraic terms separated by addition or subtraction. Okay, so those are binomials. When you expand it, it means when you have that binomial and it's to a power outside the parentheses. So, for example, a plus b to the 0, or a plus b the sum to the first, and so on. Then that's binomial expansion, multiplying all this out. Now, that could get pretty tedious if we actually had to multiply it out, but there's a lot of patterns to it that make it really super duper easy. All right, now, there are really 2 types of patterns we need to analyze. And analyze the coefficients and the variables and their exponents. All right, so look at this. Some of these that you know. A plus b to the 0. What is anything to the 0? 1. Cool. That's the easiest expansion of all. The second easiest expansion of all is what's a plus b to the first? A plus b. Now you can notice then that the coefficients are 1 and 1. Well done. Say coefficients are 1, 1 and 1. Why is that so thick? Cool. All right. Now let's go to a plus b all squared. I might need a little more room for that. But if you talk a plus b all squared, isn't it a plus b times a plus b? All right. So when I multiply that out, what do I get? A squared. Okay, I'm with you. Go ahead, keep going. Sorry. A times a is a squared. Plus 2ab plus b squared. Now notice the coefficients there are actually 1, 2, and 1. Yeah? Now, you're going to start to see a pattern to the coefficients, and we're going to show this in what's called Pascal's triangle. All right? In Pascal's triangle, move this over here, the coefficients show up in Pascal's triangle. This day is going bad, but I don't care because it's going to be a great day tomorrow. So take it. All right, so anyway, Pascal's triangle looks like this. In the pattern, you can see then is on the diagonals, it's obviously, the diagonals are always 1. That's on both sides. So the diagonals are always 1 on the outsides, yeah. What do you notice about the next row, or next diagonal column? These go 1, 2, 3, 4, and so on. Okay, so these on this diagonal, they go up by 1 each time. This is like total nerd out time. Pascal's triangle is like the math person's favorite thing to think about. Okay, are you cool so far? Now the actual way you get any next number in Pascal's triangle is really the sum of the two above it. That's the classic kind of way to find a number. If you notice, that 2 comes from adding 1 and 1. Yeah? 1 and 1 is 2. Or here, 1 and 2 is 3. And 2 and 1 is 3. So you can always add the 2 directly diagonally above it to get the next number. Cool? Now, with all those patterns, you should be able to tell me what's the next row. What are the diagonals? 1. And then if you add the 2, you get 4. And that also carries through that 1, 2, 3, 4 pattern. What about the middle? 6. And then 4. That's that also diagonal pattern here, going up by 1. And 1. What's the next row? You do the next row on your own. And I'm about to blow your mind, man. Actually, only some of your people are. What's the next row? James, what's the next row? Man. 5. Oh, I already got 1, 4, 6, 4, 1. 1, 5. 10. 10. 1. Okay. Now that's cool, and those are the main things. But just for total math nerd time, check this out. I'm gonna need to do this in purple or something cool. If I add through this space, that's a 1, yeah? And then if I add this, that's so here's a 1, obviously. 1, that's a 2. Then if I add these, that's a 3. And if I add these, that's 1, 3, 1, that's 5. And if I add these, it's 1, 4, 3, and that is 8. You notice anything? Please tell me somebody. Okay, that is actually the most famous sequence of numbers in all of numbers. What is it?
Fibonacci.
Yeah, that's Fibonacci. Fibonacci is in the Pascal's triangle. Okay, so what's the idea on the next number in Fibonacci? Yeah, you add the previous 2 numbers to get the next number. So 1 and 1 is 2, 1 and 2 is 3, 2 and 3 is 5, 3 and 5 is 8. Fibonacci. Fibonacci, who cares? So it's about Fibonacci. Okay, so you could go on, there are whole classes on Fibonacci. You could watch hours of video on Fibonacci, but that tree right there, the next time it puts a branch out, do you think it'll just do it so randomly? Or is it going to put the branch in a place that will maximize how much sun it'll get? Well, it'll be exactly that. And how it does each branch, Fibonacci. If I were to count the branches of a tree, or the slices of an orange, or the nautilus of segment, or the beauty of the Parthenon, all Fibonacci. gosh, so many Fibonacci's. We really should just take a huge day to go over Fibonacci and the golden ratio. But I digress. Today is binomial expansion, so let's go. Now, I said to get a binomial expansion without actually multiplying a plus b times itself over and over, which would be a total drag, we're going to analyze patterns. The coefficient pattern is Pascal's triangle. If you can crank out Pascal's triangle, which most people can do 10 rows in a minute easy, then you have the coefficients. You can see the coefficients in a plus b squared were exactly like Pascal's triangle. Okay? Shucks. So in a plus b cubed, if I want a plus b cubed, then the coefficients to the row with the 3 in it, those will be the coefficients in a plus b cubed if I were to multiply it out, which I don't want to do because that's a drag. You follow me? So it's going to be 1 algebraic term, 3 algebraic term, 3 algebraic term, and 1. And now we have to figure out, okay, after the coefficients, then I had a bunch of a's and b's, right? What about the coefficients, or the variables, sorry. For the variables, look at the a's. When we did a plus b squared, it started with a squared, then it was a to the first, and then it was no a's. So it seems like the a's decrease in power every time. They start with the power you're looking at, so in this case a squared, and then they go down by 1 each time. So a starts at the given power and goes down 1 each time. Now in this case, a plus b cubed means that a will start at a cubed, and then we'll go with squared a, and then a to the 0 is just not a 1. No. You with me? Okay. What do you notice about b? B starts at nothing, and then b to the first, and then b squared. B increases in power by 1, starting at 0. So in a plus b cubed, we'll start with no b's. Then we'll get b to the first, or b to the 1, and then we'll get b squared, and we'll end at cubed. You avoid all that a plus b cubed stuff. Or a plus b times a plus b times a plus b stuff. You with me? So coefficients, a exponents go down, b exponents go up. So with that said then, would you try x plus y to the 4th? Or let's try, actually. X plus y to the 4th. What row will we need a Pascal's triangle for the coefficient? We'll need to go till you see a 4 here. So we need to keep going one more row. What's the next row? Right. Add the 2 diagonally above it to get the next, and you always start with 1 on the outside. Okay, so there's our coefficients. And let's start. The first coefficient is 1, and the variable that goes with 1 is x to the 4th, and no y's. Plus, the next coefficient is 4. X changes to x to the 3rd, or cubed, and now we get y's instead of y to the 0. Now we're getting a y to the 1, yeah? What's your next term, or the 3rd term? 6x squared y squared plus 4 1y cubed, or xy cubed, plus 1 y to the 4th. Would you notice, write yourself a note here, notice that in each term, the exponents always add to 4. Now that had to do with the fact that we were doing x plus y to the fourth. If you look at the one we just did, here, if we look at a return, the exponents always add to 3, because we did a plus b to the third. That'll be the case. It'll always be the case that the exponents add to whatever power you are doing in the problem. All right? Would you try this one? Example 2. Try it on your own, please, and then we'll talk about it. Feel free to talk it over with your math amigos. Change the settings on this board. I'm so crazy. Okay. So it feels like if we're going to the 6, don't you need the row with the 6 in it in the second spot, yeah? Okay. I can keep going, but I really just want the fourth term. So once I saw the fourth coefficient, I stopped. So what's the fourth coefficient is 20. Now, if you want to write all the other stuff, fine. But if you can jump to it, fine. S to the what? Third. It would start at 6, then go 5, 4, 3. Perfect. Once you know 3, then you can either count up to t, or you could say they need to total to 6, right? Either way, t's exponent is 3. Okay? It's actually easiest to find this one first. The second exponent is always term number minus 1. And the first exponent is total power minus second exponent. That's actually where the formula for the binomial theorem comes from. All right, last but not least, let's talk about yucky ones. This one is a little yucky because of the negative. So be careful. So write yourself a note here. Negative, careful there. All right, so do you have somewhere in your paper the row we're going to need of Pascal's triangle? You have it? I don't have it. So it's something like 1, 7, 21, 35, 35. Did I make a mistake? 21, 7, 1. Okay, so there's your coefficients. Cool. All right, so your first term. Ms. Laura, what is it?
1, 8, and 7.
Wonderful. Okay. The stuff gets funky in the second term. This is really like a plus negative b to the 7th. So when we get to the second term, I think we can all agree the coefficient will be 7. We're cool? All right. And a is to the 6th. The weird part is the next term. It's not b to the 1st, but negative b to the 1st. The third term, what's the coefficient? 21, a to the fifth, and negative b to the second. Then 35, a to the fourth, negative b to the third, then 35, a to the third, negative b to the, sorry, a to the third, negative b to the fourth. We're getting there. 21, a to the second, negative b to the fifth, plus 7, a to the first, negative b to the sixth, plus 1, b, negative b to the seventh. Now, unfortunately, we're going to have to clean this up. What are you going to reckon about the signs each time? They're going to alternate or change, yeah. So a to the seventh minus 7a to the sixth b, because that's a negative to an odd power. But then plus 21a to the fifth b squared, because a negative to an even power is positive. Then negative 35a to the fourth b cubed plus 35a cubed b to the fourth minus 21a squared b to the fifth plus 7ab to the sixth and minus b to the seventh. Cool. All right. So when I did a plus b, a minus b to the seventh, I have 1, 2, 3, 4, 5, 6, 7, 8 terms. When I did a plus b to the fourth, if I did a plus b to the sixth, I would have 7 terms. Generally, you'll always have one more than the power you're doing. So a plus b to the n, you'll have n plus 1. All right, that's it. Are you with me? Cool. Would you do this problem to get the problem set somewhere? Feel free to go into that. When you get the answer, come on up, and we'll actually give you. Never mind. Juniors, I need to. So, juniors, I need to give you tomorrow's inset. Juniors, raise your hand. 2, 3. This is what we'll be doing tomorrow. It'll be good test prep today. Juniors. Oh, heck. I agree with that. Juniors. Yes, seniors are up too. All seniors, people. Okay. All right. When you get your answer, come show me. And okay, I hope that's right. What did you get? Is it right? You think so?
Yeah, because if you go to the physics section here, it would say
No, but you must trust. You must trust. I just know you. They should add 2 seconds.
Oh.
See that one should be on. Thank you. And what sign? Looks like there's just one G. No negative. There's no negative.
Like this? Oh, I mixed it up on the last.
Wow, way to go, Overachiever. Not really what I wanted.
Oh, you went with this term. I should look at that.
Really overachieved. Good job.
Good job.
You.
Can I get tests for Wednesday, Thursday,
Friday's the test. Oh, I don't actually. Wow. Way to go, Overachiever.
Oh, is it the big
Fifth term.
Oh, okay.
That should be a Z, not an X.
Oh, my bad.
Yeah. You want to just throw that?
Oh, sure.
Sure. It doesn't say expand the heck out of this thing. It says the fifth term, people. What the heck? Okay. Why you people waste your time? Okay. Thank you. So 1, 2, 3, 4.
Then
All righty. So it's just gonna be a little small senior slash teacher group tomorrow. That'd be cool.
I really like that. We have lunch. We really have lunch.
The test on Friday is through 70.
You're vegetarian. You would be.
Let me think about that.
You would be vegetarian. That's so cool. On my head. So loud.
It's got at least 73, which is polygon area. I don't know if it has Kramer's rule or not, and I don't think it does. I think the test is through 73, but I'll check that. Okay. Who just asked me for? Oh, okay. All right. Hello. Yes. Sorry. 76.
We don't hate the gays.
What?
I work at Chick-fil-A. I don't hate the gays. Chick-fil-A does not hate the gays,
I
guys.
don't really like the.
I get harassed for this at
Let's just.
Red Rocks. Yeah, we sell sandwiches at Red Rocks. People are like, Chick-fil-A to go for a 10. Chick-fil-A hates the gays. And I'm like, this makes sense.
Let's just. Okay then. All right. 76. Enough. Let's just work, shall we? 76.
What? Yeah,
One. I don't know if I have. Hello. Did you have trouble with the delay?
Yeah, no, I was confused.
All right.
You did just incredibly overreact.
You said
Wednesday.
Wednesday. Okay.
I'm driving. Take a marathon. Get to drive through Miami is brutal. I went to Boise, Idaho, and I jumped there.
Wednesday.
To look there? Well, I went, yeah, for soccer. Let's do it for soccer. Did you like it? It's okay. Someone suggested